Hello viewers, welcome to my channel Online Biology Tutorials. In today's live, we will be reading chapter 9 Light, Reflection and Refraction. This is class 10th science chapter taken from NCERT which is being followed in the CBSE board. In case you are interested in hearing the audio of first 8 chapters, the playlist has already been uploaded. I hope the screen is clear to everyone. So let's begin with the reading of light, refraction, reflection, and refraction. We see a variety of objects in the world around us. However, we are unable to see anything in a dark room. On lighting up the room, things become visible. What makes things visible? During the day, the sunlight helps us to see the objects. An object reflects light that falls on it. This reflected light, when received by our eyes, enable us to see things we are able to see through a transparent medium as light is transmitted through it. There are a number of common wonderful phenomena associated with light, such as image formation by mirrors, the twinkling of stars, the beautiful colors of a rainbow, bending of light by a medium, and so on. A study of the properties of light helps us to explore them. By observing the common optical phenomena around us, we may conclude that light seems to travel in straight lines. The fact that a small source of light casts a sharp shadow of an opaque object points to this straight line path of light, usually indicated as a ray of light. Now, this block, small block, where it is written more to know. If an opaque object on the path of light becomes very small, light has a tendency to bend around it and not walk in a straight line, an effect known as the diffraction of light. Then the straight line treatment of optics using ray fails. To explain phenomena such as diffraction, light is thought of as a wave, the details of which you will study in higher classes. Again, at the beginning of the 20th century, it became known that the wave theory of light often becomes inadequate for treatment of the interaction of light with matter, and true nature of light continued for some years till a modern quantum theory of light emerged in which light is neither a wave or nor a particle. The new theory reconciles the practical properties of light with the wave nature. R.N. Sahu, this is 10th generation. In this chapter, we shall study the phenomena of reflection and refraction of light using the straight line propagation of light. These basic concepts will help us in the study of some of the optical phenomena in nature. We shall try to understand in this chapter the reflection of light by spherical mirrors and refraction of light and their application in real life situations. 9.1 Reflection of light. A highly polished surface, such as mirror, reflects most of the light falling on it. You are already familiar with the laws of the reflection of light. Let us recall these laws. The angle of incidence is equal to the angle of reflection, and the incident ray, the normal, to the mirror at a point of incidence, and the refracted ray all lie in the same plane. These laws of reflection are applicable to all types of reflecting surfaces, including spherical surfaces. You are familiar with the formation of image by a plane mirror. What are the properties of the image? Image formed by a plane mirror is always virtual and erect. The size of an image is equal to that of the object. The image formed is as far behind the mirror as the object is in front of it. Further, the image is laterally inverted. How would the images be when the reflecting surfaces are curved? Let us explore. This is the live reading of this chapter 9. Activity 9.1. Take a large shining spoon. Try to view your face in its curved surface. Do you get the image? Is it smaller or larger? Move the spoon slowly away from your face. Observe the image. How does it change? Reverse the spoon and repeat the activity. How does the image look like now? Compare the characteristics of the image on the two surfaces. The curved surface of a shiny spoon could be considered as a curved mirror. The most commonly used type of curved mirror is the spherical mirror. The reflecting surface of such mirrors can be considered to form a part of the surface of a sphere. Such mirrors, whose reflecting surfaces are spherical, are called spherical mirrors. We shall now study about spherical mirrors in some detail. 9.2 Spherical mirrors. The reflecting surface of a spherical mirror may be curved inwards or outwards. A spherical mirror whose reflecting surface is curved inwards, that is, faces towards the center of the sphere, is called a concave mirror. A spherical mirror whose reflecting surface is curved outwards is called a convex mirror. The symmetric representation of these mirrors is shown in figure 9.1. You may note in these diagrams that the back of the mirror is shaded. Aryan Sahu, yes, most of the times I do daily live class in the evening and I explain certain topics also. But today's live is the audio reading, so I will not be doing any explanation in between. I have already recorded a video series, explanatory ones, on life processes and heredity chapter. In case you are interested, you can visit the playlist of my section. You may now understand that the surface of the spoon curved inwards can be approximated to a concave mirror, and the surface of the spoon bulged outwards can be approximated to a convex mirror. Aryan Sahu, I only teach science. Before we move further on spherical mirrors, we need to recognize and understand the meaning of a few terms. These terms are commonly used in discussions about spherical mirrors. The center of the reflecting surface of a spherical mirror is a point called the pole. It lies on the surface of the mirror. The pole is usually represented by the letter P. In figure 9.1, A is concave mirror, this one, and this one is the convex mirror. Next page. I hope the screen is clear to everybody. The reflecting surface of a spherical mirror forms a part of a sphere. This sphere has a center. This point is called the center of curvature of the spherical mirror. It is represented by the letter C. Please note that the center of curvature is not a part of the mirror. It lies outside its reflecting surface. The center of curvature of a concave mirror lies in front of it. However, it lies behind the mirror in case of a convex mirror. You may note that this in figure 9.2a and b. The radius of a sphere of which the reflecting surface of a spherical mirror forms a part is called the radius of curvature of the mirror. It is represented by the letter r. You may note that the distance PC is equal to the radius of curvature. Imagine a straight line passing through the pole and the center of curvature of a spherical mirror. This line is called the principal axis. Remember that principal axis is normal to the mirror at its pole. Let us understand an important term related to mirrors through an activity. Activity 9.2. Caution, do not look at the sun directly or even into a mirror reflecting sunlight. It may damage your eyes. Hold a concave mirror in your hand and direct its reflecting surface towards the sun. Direct the light reflected by the mirror onto a sheet of paper held close to the mirror. Move the sheet of a paper back and forth gradually until you find on the paper sheet a bright, sharp spot of light. Hold the mirror and the paper in the same position for a few minutes. What do you observe? The paper at first begins to burn, producing smoke. Eventually, It may even catch fire. Why does it burn? The light from the sun is converged at a point as a sharp, bright spot by the mirror. In fact, this spot of light is the image of the sun on the sheet of paper. This point is the focus of the concave mirror. The heat produced due to the concentration of sunlight ignites the paper. The distance of this image from the position of the mirror gives the approximate value of focal length of the mirror. Let us try to understand this observation with the help of a ray diagram. Observe figure 9.2a closely. A number of rays parallel to the principal axis are falling on a concave mirror. Observe the reflected rays. These are all meeting, intersecting at a point on the principal axis of the mirror. This point is called the principal focus of the concave mirror. Similarly, observe figure 9.2b. How are the rays parallel to the principal axis reflected by a convex mirror? The reflected rays appear to come from a point on the principal axis. This point is called the principal focus of the convex mirror. The principal focus is represented by the letter F. The distance between the pole and the principal focus of a spherical mirror is called the focal length. It is represented by the letter small f. So here is the diagram which is given to you. One is for the concave mirror and this is for the convex mirror. So this is converging one and this is diverging because after striking the mirror, they are diverging away. So let's start with this page now. The reflecting surface of a spherical mirror is by and large spherical. The surface then has a circular outline. The diameter of the reflecting surface of the spherical mirror is called its aperture. In figure 9.2, distance Mn represents the aperture. We shall consider in our discussion only such spherical mirrors whose aperture is much smaller than its radius of curvature. Is there a relationship between the radius of curvature capital R and the focal length small f of a spherical mirror? For spherical mirrors of small apertures, the radius of curvature is found to be equal to twice of the focal length. We put this as capital R is equals to 2f. This implies that the principal focus of a spherical mirror lies midway between the pole and the center of curvature. 9.2.1 Image formation by spherical mirrors. You have studied about the image formation by plane mirrors. You also know the nature, position, and relative size of the images formed by them. How about the images formed by spherical mirrors? How can we locate the image formed by a concave mirror for different positions of the object? Are the images real or virtual? Are they enlarged, diminished, or have the same size? We shall explore this with an activity. Activity 9.3. You have already learned a way of determining the focal length of concave mirror. In activity 9.2, you have seen that the sharp, bright spot of light you got on the paper is in fact the image of the sun. It was a tiny, real, inverted image. You got the approximate focal length of the concave mirror by measuring the distance of the image from the mirror. Take a concave mirror, find out its approximate focal length in the way described above. Note down the value of focal length. You can also find it out by obtaining image of a distant object on a sheet of paper. Mark a line on a table with a chalk. Place the concave mirror on a stand. Place the stand over the line such that its pole lies over the line. Draw with chalk two or more lines parallel to the previous line such that the distance between any two successive lines is equal to the focal length of the mirror. These lines will now correspond to the positions of the points P, F, and C respectively. Remember, for a spherical mirror of small aperture, the principal focus F lies midway between the pole P and the center of curvature C. Keep a bright object say a burning candle at a position far beyond C. Place a paper screen and move it in front of the mirror till you obtain a sharp, bright image of the candle flame on it. Observe the image carefully. Note down its nature, position, and relative size with respect to the object size. Repeat the activity by placing the candle A just beyond C, at C, between F and C, at F, and between P and F. In one of the cases, you may not get the image on the screen. Identify the position of the object in such a case. Then look for its virtual image in the mirror itself. Note down and tabulate your observations. Next page. You will see in the above activity that the nature, position, and the size of the image formed by a concave mirror depends on the position of the object in relation to points P, F, and C. The image formed is real for some positions of the object. It is found to be virtual image for a certain other position. The image is either magnified, reduced, or has the same size depending on the position of the object. A summary of these observations is given for your reference in table 9.1. So, table 9.1 is very important and you should learn so that you should be able to solve all the numericals. So, if you place your object at infinity, then image will be formed at the focus F. The size of the image will be highly diminished. It will be point size and the image will be real and inverted. If you place the object at beyond C, then image will be formed between F and C. The image will be diminished, real and inverted. If you place the object at C, image will also be formed at C. It will be of the same size, real and inverted. If you place the object between C and F, image will be formed beyond C. The image will be enlarged, real and inverted. If you place the object at F, the image will be formed at infinity and the image would not be formed in this case. If you place the object between P and F, image will be formed behind the mirror. The image will be enlarged, virtual and erect. This is a special case of concave mirror, the only exception. You need to understand it thoroughly. Now, 9.2.2, representation of images formed by spherical mirrors using ray diagrams. We can also study the formation of images by spherical mirrors by drawing ray diagrams. Consider an extended object of finite size placed in front of a spherical mirror. Each small portion of the extended object acts like a point source. An infinite number of rays originate from each of these points. To construct the ray diagrams in order to locate the image of an object, an arbitrarily large number of rays emanating from a point could be considered. However, it is more convenient to consider only two rays for the sake of clarity of the ray diagram. These rays are so chosen that it is easy to know their directions after reflection from the mirror. The intersection of at least two reflected rays give the position of image of the point object. Any two of the following rays can be considered for locating the image. So, 1. A ray parallel to the principal axis after reflection will pass through the principal focus in case of a concave mirror or appear to diverge from the principal focus in case of a convex mirror. This is illustrated in 9.3 A and B. So this one and this one. Next one. A ray passing through the principal focus of a concave mirror or a ray which is directed towards the principal focus of a convex mirror after reflection will emerge parallel to the principal axis. This is illustrated in figure 9.4a and b. A ray passing through a center of curvature of a concave mirror or directed in the direction of the center of curvature of a convex mirror after reflection is reflected back along the same path. This is illustrated in 9.5a and b. The light rays come back along the same path because the incident rays fall on the mirror along the normal to the reflected surface. Shreyash, welcome. Now, the next point, we are done till 9.5. So, a ray incident obliquely to the principal axis towards at point P, pole of the mirror on the concave mirror or a convex mirror is reflected obliquely. The incident and the reflected rays follows the rays of reflection at the point of incidence point P, making equal angles with the principal axis. Twinkle, this is just the live reading of this book. Explanatory videos will be coming some other day, not today's. So there are students who just want to revise. So I'm reading for all those students as it was requested. Remember that in all the above cases, the laws of reflection are followed. At the point of incidence, the incident ray is reflected in such a way that the angle of reflection equals the angle of incidence. Image formed by concave mirror. Figure 9.7 illustrates the lay diagrams for the formation of image by a concave mirror for various positions of the object. Activity 9.4. Draw neat ray diagrams for each position of the object shown in table 9.1. You may take any two of the rays mentioned in the previous section for locating the image. Compare your diagram with those given in figure 9.7. Describe the nature, position, and relative size of the image formed in each case. Tabulate the results in a convenient format. Use of concave mirrors. Concave mirrors are commonly used in torches, searchlights, and vehicle headlights to get powerful parallel beam of lights. They are often used as shaving mirrors to see a large image of the face. The dentists use concave mirrors to see large images of the teeth of the patients. Large concave mirrors are used to concentrate sunlight to produce heat in solar furnaces. Image formation by convex mirror. We studied the image formation by the concave mirror. Now we shall study the formation of image by a convex mirror. Activity 9.5. Take a convex mirror, hold it in one hand, hold a pencil in the upright position in the other hand. Observe the image of the pencil in the mirror. Is the image erect or inverted? Is it diminished or enlarged? Move the pencil away from the mirror slowly. Does the image become smaller or larger? Repeat this activity carefully. State whether the image will move closer to or further away from the focus as the object is moved away from the mirror. We consider two positions of the object for studying the image formed by a convex mirror. First is when the object is at infinity, and the second position is when the object is at the finite distance from the mirror. The ray diagrams for the formation of image by a convex mirror for these two positions of the object are shown in figure 9.8a and b respectively. The results are summarized in table 9.2. So 9.2, if you place the object at infinity, then at the focus or F behind the mirror will be the image. Image will be highly diminished, point size, and it will be virtual and erect. So this is for the convex mirror. If you place the object between infinity and the pole P of the mirror, then image will be formed between P and F behind the mirror. Image will be diminished, virtual, and erect. You have so far studied the image formation by a plane mirror, a concave mirror, and a convex mirror. Which of these mirrors will give the full image of a large object? Let us explore through an activity. Activity 9.6. Observe the image of a distant object, say a distant tree, in a plane mirror. Could you see a full length image? I hope the screen is clear. Try with plane mirrors of different sizes. Did you see the entire object in the image? Repeat this activity with a concave mirror. Did the mirror show full length image of the object? Now try using a convex mirror. Did you succeed? Explain your observations with reasons. Students, all the students who are listening to this live, I have done a few lives where I have made you understand about tropic and nastic movements, right? We have also explained phytohormones. In case you are interested, you can come up to the live, and the full explanatory videos on life processes and heredity with numericals are also being uploaded in the playlist. You can explore it if you are looking further for it. You can see a full length image of a tall building or a tree in a small convex mirror. One such mirror is fitted in a wall of Agra Fort facing Taj Mahal. If you visit the Agra Fort, try to observe the full image of Taj Mahal. To view distinctly, you should stand suitably at the terrace adjoining the wall. Uses of convex mirrors. Convex mirrors are commonly used as a rear view wing mirrors in vehicles. These mirrors are fitted on the sides of the vehicle, enabling the driver to see the traffic behind him or her to facilitate safe driving. Convex mirrors are preferred because they always give an erect, though diminished image. Also, they have a wider field of view as they are curved outwards. Thus, convex mirrors enable the driver to view much larger area than would be possible with a plane mirror. Next, in-text questions. Define the principal focus of a concave mirror. 2. The radius of curvature of a spherical mirror is 20 centimeter. What is the focal length? 3. Name a mirror that can give an erect and enlarged image of an object. 4. Why do we prefer a convex mirror as a rear view mirror in the vehicles? 9.2.3 Sign convention for reflection by spherical mirrors. While dealing with the reflection of light by spherical mirrors, we shall follow a set of sign conventions called the New Cartesian sign convention. In this convention, the pole of the mirror is taken as the origin. The principal axis of the mirror is taken as the x-axis of the coordinate system. The conventions are as follows. The object is always placed to the left of the mirror. This implies that the light from the object falls on the mirror from the left hand side. All distances parallel to the principal axis are measured from the pole of the mirror. All the distances measured to the right of the origin along the x-axis are taken as positive, while those measured to the left of the origin along minus x-axis, so it was positive, it was negative, are taken as negative. Distances measured perpendicular to and above the principal axis along plus y-axis are taken as positive. Distances measured perpendicular to and below the principal axis along minus y-axis are taken as negative. Light is one of the lengthiest and the chapter with maximum weightage, so you should practice all the Cartesian signs well, so that you should not make any mistake in the numericals, because in case you take any of the sign incorrectly, the end result would be wrong only. The new Cartesian sign convention described above as illustrated in figure 9.9 for your reference. These sign conventions are applied to obtain the mirror formula and solve related numerical problems. 9.2.4 Mirror formula and magnification. In a spherical mirror, the distance of the object from its pole is called the object distance or small u. The distance of the image from the pole of the mirror is called the image distance small v. You already know that the distance of the principal focus from the pole is called the focal length or small f. There is a relationship between these three quantities given by the mirror formula, which is expressed as 1 by V plus 1 by U is equals to 1 by F. This formula is valid in all the situations for all the spherical mirrors. For all positions of the object, you must use the new Cartesian sign convention while substituting numerical values for U, V, F, and R in the mirror formula for solving the problems. Magnification Magnification produced by a spherical mirror gives the relative extent to which the image of an object is magnified with respect to the object size. It is expressed as the ratio of the height of the image to the height of the object. It is usually represented by the letter small m. Mayank Kaushik, this is audio. In this video, no explanation will be done as you can go through the thumbnail that has already been posted. If small h is the height of the object and h dash is the height of the image, then the magnification m produced by a spherical mirror is given by the formula m is equals to height of the image h dash divided by height of the object h. The magnification m is also related to the object distance u and the image distance small b. It can be expressed as magnification, which is written as a small m, is equals to h dash by h is equals to minus v upon u. You may note that the height of the object is taken to be positive as the object is usually placed above the principal axis. The height of the image should be taken as positive for virtual images. However, it is to be taken as negative for real images. A negative sign in the value of the magnification indicates that the image is real. A positive sign in the value of the magnification indicates that the image is virtual. Example 9.1. A convex mirror used for rear view on an automobile has a radius of curvature of 3 meter. If a bus is located at 5 meter from this mirror, find the position, nature, and size of the image. So radius of curvature r is given to you plus 3 meter. Object distance u is minus 5 because it is on the minus x-axis 5 meter. Image distance v you need to calculate, and height of the image is h dash. Mayank Kaushik, this is not the explanatory video. In case you are looking for explanation, I am not doing the explanation today. As you can go through the thumbnail, it is the audio of this chapter. Focal length f is equals to r by 2. So after calculation, you will get the value of plus 1.5 meter. A convex mirror. So as the principal focus of a convex mirror is behind the mirror. We know this formula. Focal length f is equals to r by 2. So this way you will be calculating. We know already this formula 1 by v plus 1 by u is equals to 1 by f. So after putting the values, you will be able to calculate v is equals to plus. So sign conventions are important. It is going to be plus 1.15 meter. So image is 1.15 meter at the back of the mirror. Magnification can be calculated with this formula. So once you put up the values, you will get plus 0.23. The image is going to be virtual, erect, and smaller in size by a factor of 0.23. So whatever you have learned through ray diagrams, you should correlate here with your values as well. I'll explain this when I will be doing a live on this chapter. Example 9.2. An object 4 centimeter in size is placed at 25 centimeter in front of a concave mirror of a focal length 15 centimeter. At what distance from the mirror should a screen be placed in order to obtain a sharp image? Find the nature and the size of the image. So solution. H is given to you plus 4 centimeter. Distance u is minus 25 centimeter. Focal length is minus 15 centimeter. You need to calculate small b. You need to calculate h dash. So we know the formula 1 by v plus 1 by u is equals to 1 by f. So after putting the values, you will be able to calculate v is equals to minus 37.5 centimeter. The screen should be placed at 37.5 centimeter in front of the mirror. The image is going to be real. For magnification, we already have the formula m is equals to h dash upon h. We need to calculate h dash, so it will be calculated with this mh, and for m we will be substituting it with minus v by u. So after placing the values, the height will be calculated as minus 6 centimeters. So image, because if it is beneath the axis, the principal axis, the image is going to be inverted and the size is bigger. That is why it is going to be enlarged. In text question, find the focal length of a convex mirror whose radius of curvature is 32 centimeter. A concave mirror produces 3 times magnified or enlarged rear image of an object placed at 10 centimeter in front of it. Where is the image located? 9.3, refraction of light. Light seems to travel along straight line paths in a transparent medium. What happens when light enters from one transparent medium to another? Does it still move along a straight line path or change its direction? We shall recall some of our day to day experiences. You might have observed that the bottom of a tank or a pond containing water appears to be raised. Similarly, when a thick glass slab is placed over some printed matter, the letters appear raised when viewed through a glass slab. Why does it happen? Have you seen a pencil partly immersed in water in a glass tumbler? It appears to be displaced at the interface of air and water. You might have observed that the lemon kept in water in a glass tumbler appears to be bigger than its actual size when viewed from the sides. How can you account for such experiences? Let us consider the case of a apparent displacement of a pencil partly immersed in water. The light reaching you from the portion of the pencil inside water seems to come from a different direction compared to the part above water. This makes the pencil appear to be displaced at the interface. For similar reasons, the letter appear to be raised when seen through a glass slab placed over it. Does a pencil appear to be displaced to the same extent? If instead of water we use liquids like kerosene or turpentine, will the letters appear to rise to the same height if we replace a glass slab with the transparent plastic slab? Prince, you can leave. Nobody has asked you to join it. You can join the physics wala. The ones who are interested can remain here. So we have read till here. You will find that the extent of the effect is different for different pair of media. These observations indicate that light does not travel in the same direction in all media. It appears that when traveling obliquely from one medium to another, the direction of propagation of light in the second medium changes. This phenomena is known as refraction of light. Let us understand this phenomenon further by doing a few activities. So we are here on these activities now. Activity 9.7, place a coin at the bottom of a bucket filled with water. With your eye to a side above water, try to pick up the coin in one go. Did you succeed in picking up the coin? Repeat the activity. Why did you not succeed in doing it in one go? Ask your friend to do it. Compare your experience with theirs. Activity 9.8, place a large, shallow bowl on a table and put a coin in it. Move away slowly from the bowl. Stop when the coin just disappears from your sight. Ask a friend to pour water gently into the bowl without disturbing the coin. Keep looking for a coin from your position. Does the coin becomes visible again from your position? How could this happen? The coin becomes visible again on pouring water into the bowl. The coin appears slightly raised above its actual position due to refraction of light. Activity 9.9, draw a thick straight line in ink over a sheet of white paper placed on a table. Place a glass slab over the line in such a way that one of its edges makes an angle with the line. Look at the portion of the line under the slab from the slides. from the sides. What do you observe? Does the line under the glass slab appear to be bent at the edges? Next, place the glass slab such that it is normal to the line. What do you observe now? Does the part of the line under the glass slab appear bent? Look at the line from the top of the glass slab. Does the part of the line beneath the slab appear to be raised? Why does this happen? 9.3.1 Refraction through a rectangular glass slab. All the students who are listening to this live, thank you. In tomorrow's live, I will let you know how you can perform practical at your own place using the labs which are available over net. It has all the practicals for class 10, so stay connected for tomorrow's live. 9.3.1 Refraction through a rectangular glass slab. To understand the phenomenon of reflection of light through a glass slab, let us do an activity. So we have reached here, activity 9.10. Fix a sheet of white paper on a drawing board using drawing pins. Place a rectangular glass slab over the sheet in the middle. Draw the outline of the slab with a pencil. Let us name the outline as ABCD. Take four identical pins. Fix two pins, say E and F vertically such that the line joining the pins is inclined to the edge AB. Look for the images of the pins E and F through the opposite edge. Fix two other pins, say G and H, such that these pins and the images E and F lie in a straight line. Remove the pins and the slab. Join the positions of tip of the pins E and F and produce the line up to AB. Let EF meet AB at O. Similarly, join the positions of tip of the pins G and H and produce it up to the edge CD. Let HG meet CD at O dash. Join O and O dash. Also produce EF up to P as shown by a dotted line in figure 9.10. This is a lengthy chapter. I hope you might have got a part of it in the test, and a complete chapter will be coming in the half yearlies. In this activity, you will note the light ray has changed its direction at point O and O dash. Note that both the points O and O dash lie on surfaces separating two transparent media. Draw a perpendicular N dash to AB at O and another perpendicular M dash to CD at O dash. The light ray at point O has entered from a rarer medium to a denser medium, that is from air to the glass. Note that the light ray has bent towards the normal. At O dash, the light ray has entered from glass to air. That is, from a denser medium to a rarer medium. The light here has bent away from the normal. Compare the angle of incidence with the angle of refraction at both refracting surfaces AB and CD. In figure 9.10, a ray EO is obliquely incident on the surface AB called the incident ray. OO dash is the refracted ray and O dash H is the emergent ray. You may observe that the emergent ray is parallel to the direction of the incident ray. Why does it happen so? The extent of bending of the ray of light at the opposite parallel faces AB, air glass interface, and CD, glass air interface of the rectangular glass slab is equal and opposite. That is why the ray emerges parallel to the incident ray. However, the light ray is shifted sideward slightly. What happens when a light ray is incident normally to the interview of two media? Try and find out. Now, you are familiar with the refraction of light. Refraction is due to the change in the speed of light as it enters from one transparent medium to another. Experiments show that refraction of light occurs according to certain laws. The following are the laws of refraction of light. 1. The incident ray, the refracted ray, and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. The ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for the light of a given color and for the given pair of media. This law is also known as Snell's law of reflection. This is true for angle 0, I is lesser than 90 degree. So if I is the angle of incidence and R is the angle of refraction, then sin I by sin R will be a constant. This constant value is called refractive index of the second medium with respect to the first. Let us study about refractive index in some detail. 9.3.2, read the refractive index. You have already studied that a ray of light that travels obliquely from one transparent medium into another will change its direction in the second medium. The extent of the change in direction that takes place in a given pair of media may be expressed in terms of refractive index, the constant appearing on the right hand side of equation 9.4. The refractive index can be linked to an important physical quantity, the relative speed of propagation of light in different media. It turns out that the light propagates with different speeds in different media. Light travels fastest in vacuum with a speed of 3 into 10 to the power 8 meter per second. In air, the speed of light is only marginally less compared to that in vacuum. It reduces considerably in glass or water. The value of the refractive index for a given pair of media depends upon the speed of light in the two media as given below. Consider a ray of light traveling from medium 1 into medium 2 as shown in figure 9.11. Let V1 be the speed of light in media 1 and V2 be the speed of light in media 2. The refractive index of medium 2 with respect to medium 1 is given by the ratio of the speed of light in medium 1 and the speed of light in medium 2. This is usually represented by the symbol N21. This can be expressed in an equation as N21 means speed of the light in medium 1 with respect to the speed of light in medium 2, V1 by V2. By the same argument, the refractive index of medium 1 with respect to medium 2 is represented as N12. It is given by N12 speed of the light in medium 2 with respect to 1. So 2 should be spoken first, then will be speaking 1. It is going to be the reverse of the above, so it will become V2 by V1. If medium 1 is vacuum or air, then the refractive index of medium 2 is considered with respect to the vacuum. This is called the absolute refractive index of the medium. It is simply represented as N2. If C is the speed of light in air and V is the speed of light in the medium, then the refractive index of the medium N M is given by Nm is equals to speed of the light in air divided by speed of the light in the medium, that is equals to C by V. The only listener which is connected with me still, may I know your name please in the chat? The absolute refractive index of a medium is simply called its refractive index. The refractive index of several media is given in table 9.3. From the table, you can know that the refractive index of water is 1.33. This means that the ratio of the speed of light in air and the speed of light in water is equals to 1.33. Similarly, the refractive index of crown grass is 1.52. Such data are helpful in many places. However, you need not memorize the data. So table 9.3 has given you all the reflective index values for air, ice, water, alcohol, kerosene, fused quartz, turpentine oil, benzene, crown grass, Canada balsam, rock salt, carbon disulfide, dense flint glass, ruby, sapphire, and diamond. Note from table 9.3 that an optically denser medium may not possess greater mass density. For example, kerosene having higher refractive index is optically denser than water, although its mass density is less than water. More to know, of uh, the ability of a medium to refract light is usually expressed in terms of its optical density. Optical density has a definite connotation. It is not the same as mass density. We have been using the terms rarer medium and denser medium in this chapter. It actually means optically rarer medium or optically denser medium, respectively. When can we say that a medium is optically denser than the other? In comparing two media, the one with a large refractive index is optically denser medium than the other. The other medium of lower refractive index is optically rarer. The speed of light is higher in a rarer medium than the denser medium. Thus, a ray of light traveling from a rarer medium to a denser medium slows down and bends towards the normal. When it travels from the denser medium to a rarer medium, it speeds up and bends away from the normal. In text questions on the next page, question number 1. A ray of light traveling in air enters obliquely into water. Does the light ray bend towards the normal or away from the normal? Why? Light enters from air to glass having refractive index 1.5. What is the speed of light in the glass? The speed of light in vacuum is 3 into 10 to the power 8 meter per second. Find out from table 9.3 the medium having highest optical density. Also find the medium with lowest optical density. You are given kerosene, turpentine, and water. In which of these does the light travel fastest? Use the information given in table 9.3. The refractive index of diamond is 2.42. What is the meaning of this statement? 9.3.3. Refraction by spherical lenses. You might have seen watchmakers using a small magnifying glass to see tiny parts. Have you ever touched the surface of a magnifying glass with your hand? Is it plain surface or curved? Is it thicker in the middle or at the edges? The glasses used in spectacles and that by a watchmaker are examples of the lenses. What is a lens? How does it bend light rays? We shall discuss these in this section. A transparent material bound by two surfaces of which one or both surfaces are spherical forms a lens. This means that a lens is bound by at least one spherical surface. In such lenses, the outer surface would be plane. A lens may have two spherical surfaces bulging outwards. Such a lens is called a double convex lens. It is simply called a convex lens. It is thicker in the middle as compared to the edges. Convex lens converges light rays as shown in figure 9.2a. Hence, convex lenses are also called converging lenses. Similarly, a double concave lens is bound by two spherical surfaces curved inwards. It is thicker at the edges than at the middle. Such lenses diverge light rays as shown in figure 9.12b. Such lenses are also called the diverging lenses. A double concave lens is simply called the concave lens. A lens, either a convex lens or a convex lens or a concave lens, has two spherical surfaces. Each of these surfaces form a part of the sphere. The centers of these spheres are called centers of curvature of the lens. The center of curvature of a lens is usually represented by the letter C. Since there are two centers of curvature, we may represent them as C1 and C2. An imaginary straight line placing through the two centers of curvature of a lens is known as principal axis. The center point of a lens is its optical center. It is usually represented by the letter O. A ray of light through the optical center of a lens passes without suffering any deviation. The effective diameter of a circular outline of a spherical lens is called its aperture. We shall confine our discussion in this chapter to such lenses whose aperture is much less than the radius of curvature and the two centers of curvatures are equidistant from the optical center O. Such lenses are called thin lenses with small apertures. What happens when parallel rays of light are incident on a lens? Let us do an activity to understand this. Activity 9.11. Caution, do not look at the sun directly through a lens while doing this activity or otherwise you may damage your eyes with if you do so. Hold a convex lens in your hand, direct it towards the sun. Focus the light from the sun on a sheet of paper. Observe a sharp, bright image of the sun. Hold the paper and the lens in the same position for a while. Keep observing the paper. What happened? Why? Recall your experience in activity 9.2. The paper begins to burn, producing smoke. It may even catch fire after a while. Why does this happen? The light from the sun constitutes parallel rays of light. These rays were converged by the lens at the sharp, bright spot formed on the paper. In fact, the bright spot you got on the paper is a real image of the sun. The concentration of the sunlight at a point generated heat. This caused the paper to burn. Now we shall consider rays of light parallel to the principal axis of a lens. What happens when you pass such rays of light through the lens? This is illustrated for a convex lens in figure 9.12a and for concave lens in figure 9.12b. Observe 9.12a carefully. Several rays of light parallel to the principal axis are falling on a concave lens. These rays, after refraction from the lens, are converging to a point on the principal axis. This point on the principal axis is called principal focus of the lens. Let us see now the action of a concave lens. Observe figure 9.12b carefully. Hello, Mayank. Welcome to this live. Several rays of light parallel to the principal axis are falling on a concave lens. These rays, after refraction from the lens, are appearing to diverge from a point on the principal axis. This point on the principal axis is called the principal focus of the concave lens. If you pass parallel rays from the opposite surface of the lens, you get another principal focus on the opposite side. Letter F is usually used to represent principal focus. However, a lens has two principal foci. They are represented by f1 and f2. The distance of the principal focus from the optical center of a lens is called the focal length. The letter F is used to represent the focal length. How can you find the focal length of a convex lens? Recall the activity 9.11. In this activity, the distance between the position of the lens and the position of the image of the sun gives the approximate focal length of the lens. So we are coming to the next part, image formed by the lenses. Lenses formed images by refracting light. How do lenses form image? What is their nature? Let us study this for a convex lens first. Activity 9.12. Take a convex lens, find its approximate focal length in a way described in activity 9.11. Draw five parallel straight lines using chalk on a long table such that the distance between the successive lines is equal to the focal length of the lens. Mayank, whenever I will be doing the live of this chapter, you will get a notification. In case my channel is helpful, you can subscribe. But right now, this is not the explanatory video. I am here doing just the reading of this chapter. Place the lens on a lens stand. Place it on the central line such that the optical center of the lens lies just over the line. The two lines on either side of the lens correspond to F and to F of the lens respectively. Mark them with approximate letters such as 2F1, F1, F2, and 2F2 respectively. Place a burning candle far beyond 2F1 to the left. Obtain a clear, sharp image on a screen on the opposite side of the lens. Note down the nature, position, and relative size of the image. Repeat this activity by placing you can come to the whereabouts section. There my details are given, Mayank. You can check it out. Repeat this activity by placing object just behind 2F1, between F1 and 2F1, at F1, between F1 and O. Note down and tabulate your observations. The nature, position, and relative size of the image formed by convex lens for various positions of the object is summarized in the table 9.4. So they are giving you the idea for the convex lens. If you place the object at infinity, image will be formed at f2. Image will be highly diminished, point size, real and inverted. If you place the object beyond 2f1, image will be formed between f2 and 2f2. Image will be diminished, real and inverted. If you place the object at 2f1, image will be formed at 2f2. Image will be same size, real and inverted. If you place the object between f1 and 2f1, the image will be formed beyond 2f2. It will be enlarged, real and inverted. If you place the object at f1, then image will be formed at infinity and there will be image position of the image will be at infinity, but actually real image formation on the screen will not be possible. Between focus f1 and the optical center O, then image will be formed on the same side of the lens as the object. The image will be enlarged, virtual, and erect. Let us now do an activity to study the nature, position, and relative size of the image formed by the concave lens. Activity 9.13. Take a concave lens, place it on a lens stand, place a burning candle on one side of the lens, look through the lens from the other side and observe the image. Try to get the image on a screen if possible. If not, observe the image directly through the lens. Try to get the image on a screen if possible. If not, observe the image directly through the lens. Note down the nature, relative size, and approximate position of the image. Move the candle away from the lens. Note the change in the size of the image. What happens to the size of the image when the candle is placed too far away from the lens? So, Mayank, you have found out my name. Good. So 9.5 is giving you an idea about the concave lens. So if you place your object at infinity, image will be formed at f1. The image will be highly diminished, point-sized, virtual, and erect. If you place the object between infinity and optical center O, then image will be formed between f1 and the optical center O. The image will be diminished, virtual, and erect. Mayank, I hope we are living in India. Didi is the name of a female in India. What conclusion can you draw from this activity? A concave lens will always give a virtual, erect, and diminished image, irrespective of the position of the object. 9.3.5 Image formation in lenses using ray diagrams. We can represent image formation by lenses using ray diagrams. Ray diagrams will also help to study the nature, position, and relative size of the image formed by lenses. For drawing ray diagrams in lenses alike of spherical mirrors, we considered any two of the following rays. A ray of light from the object parallel to the principal axis after refraction from a convex lens passes through the principal focus on the other side of the lens as shown in figure 9.13a. In case of a concave lens, the ray appears to diverge from the principal focus located on the same side of the lens as shown in figure 9.13b. A ray of light passing through a principal focus after refraction from a convex lens will emerge parallel to the principal axis. This is shown in figure 9.14a. A ray of light appearing to meet at the principal focus of a concave lens after refraction will emerge parallel to the principal axis. This is shown in figure 9.14b. A ray of light passing through the optical center of a lens will emerge without any deviation. This is illustrated in figure 9.15a and b both. The ray diagrams for the image formation in convex lens for a few positions of the object are shown in figure 9.16. The ray diagrams representing the image formation in a concave lens for various positions of the object are shown in figure 9.17. 9.3.6 Sign convention of spherical lenses. For lenses, we follow sign conventions similar to one used for spherical mirrors. We apply the rules of signs of distances, except that all measurements are taken from the optical center of the lens. According to the convention, the focal length of a convex lens is positive and that of concave lens is negative. So you must take care to apply approximate signs for the values u, v, f, object height h, and the image height h dash. 9.3.7 Lens formula and magnification. As we have a formula for spherical mirrors, we also have formula for spherical lenses. This formula gives the relationship between the object distance u, image distance v, and the focal length f. This lens formula is expressed as 1 by v minus 1 by u is equals to 1 by f. The lens formula given above is general and is valid in all the situations for all the spherical lenses. Take proper care of the signs of different quantities while putting the numerical values for solving problem related to the lenses. So magnification in the case of lens. Magnification produced by a lens similar to that of a spherical mirror is defined as the ratio of the height of the image and the height of the object. Magnification is represented by the letter M. If h is the height of the object and h dash is the height of the image given by a lens, then the magnification produced by the lens will be calculated as height of the image divided by height of the object. So h dash upon h. Magnification produced by a lens is also related to the object distance u and the image distance v. This relationship is given as m is equals to h dash upon h is equals to v by u. So this example, I am reading it out. Example 9.3. A concave lens has focal length of 15 centimeter. At what distance should the object from the lens be placed so that it forms an image at 10 centimeter from the lens? Also find the magnification produced by the lens. So you need to calculate u here, and thereby you will be calculating the magnification. Next example 9.4. At 2 centimeter tall object is placed perpendicular to the principal axis of a convex lens of focal length 10 centimeter. The distance of the object from the lens is 15 centimeter. Find the nature, position and size of the image. Also find its magnification. So here you can calculate by placing the values. I'm just reading out the power of lens for you. You have already learned that the ability of lens to converge or diverge light rays depends on its focal length. For example, a convex lens of short focal length bends the light rays towards large angles by focusing them closer to the optical center. Similarly, concave lens of very short focal length causes high divergence than the one with longer focal length. The degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. The power of the lens is defined as the reciprocal of its focal length. It is represented by the letter P. The power P of a lens of a focal length f is given by P is equals to 1 by f. The SI unit of power of lens is diopter. It is denoted by the letter D. If F is expressed in meters, then power is expressed in diopters. Thus, 1 diopter is the power of the lens whose focal length is 1 meter. 1 diopter is equals to 1 per meter. You may note that the power of the convex lens is positive and that of a concave lens is negative. Opticians prescribe corrective lenses indicate their powers. Let us say that the lens prescribed as power equal to plus 2 diopter. This means that the lens prescribed is convex. The focal length of the lens is plus zero point 0.5 meter. Similarly, a lens of power minus 2.5 diopter has a focal length of minus zero point 0.4 meter. The lens is concave. More to know, many optical instruments consist of a number of lenses. They are combined to increase the magnification and sharpness of the image. The net power of the lens placed in contact is given by algebraic sum of the individual parts like P1, P2, P3, and so on. P is equals to P1 plus P2 plus P3. The use of powers instead of focal length for lenses is quite convenient for opticians. During eye testing, an optician puts several different combinations of corrective lenses of known power in contact inside the testing spectacles frame. The optician calculates the power of the lens required by simple algebraic addition. For example, a combination of two lenses of power plus 2 diopter and plus 0.25 diopter is equivalent to a single lens of power plus 2.25 diopter. The simple additive property of the powers of lenses can be used to design lenses system to minimize certain defects in images produced by a single lens. Such a lens system consisting of several lenses in contact is commonly used in the design of lenses of camera, microscopes, and telescopes. The students who are connected with me till now, in tomorrow's live, I will let you know about how to do different practicals which are there in the syllabus of class 10th on your own at your pace. And there is no demarcation between the theory and the practical of class 10th. So whatever is the practical syllabus given to you in your science, you need to go through all the contents because a question from the practical can also be part of your board examination. So stay connected for tomorrow's live. In case this reading part was helpful to you, you can consider subscribing. Before I end, let's read up these last three questions as the intake questions. First one is define one diopter of a power of lens. Second, a convex lens forms a real and inverted image of a needle at a distance of 50 centimeter from it. Where is the needle placed in front of the concave convex lens if the image is equal to the size of the object? Also find the power of the lens. Find the power of the concave lens of focal length 2 meter. Students, with this, we are done with the live reading of chapter 9, Reflection and Refraction. Such type of videos are requested by the children. Once they are done with the chapter, they want to hear the audio so that they should be assured that they understand the meaning of each line. In case it was helpful to you, do consider subscribing. I have already recorded the video series on life processes and heredity word problems as well. Recently in the live, I have taken phytohormones, entropic and nastic movements from the control and coordination. In case you are interested, you can definitely visit the playlist and the live playlist also. Stay connected. See you in next video. Thanks for connecting.